Hello everybody and welcome to this Head Start to A-Level Chemistry video. In this video I'm going to take a look at the quantitative chemistry, so all of the moles calculations and things to do with equations. What I'm going to be focusing on this video is the common content between combined and triple chemistry. And so this is something that everybody should have studied. I'm going to make a second video, part 2, which will focus on the quantitative chemistry that only people who did triple chemistry will have experienced. So that's going to be good revision for everybody, but particularly important for people who did combined chemistry and missed out on this content at GCSE level. The first thing to remind ourselves of is the law of conservation of mass. And that law states that atoms cannot be created or destroyed. They can only be rearranged and change which atoms are bonded together. And if we have a look at this one, where we've got calcium carbonate as a reactant, turning into calcium oxide and carbon dioxide, one of the consequences of the law of the conservation of mass is that if we start with 100 grams of calcium carbonate, we need to finish with 100 grams of product. So in this case, it will be 56 grams of calcium oxide, and therefore the difference between those two numbers, 44 grams of carbon dioxide. A second consequence of the law of conservation of mass is to do with balancing equations, because what this means in practice is the number of atoms of each type that we have in the reactants on the left-hand side has got to be equal to the number of atoms on the products on the right-hand side. So for instance, in this first example, we've got one atom of magnesium on both sides of the equation, and we've got one atom of hydrogen and chlorine on the left-hand side, and 2 and 2 on the right-hand side. So if you remember, when you are balancing equations, the only thing that you can do is have multiples of any of the formulae that appear. So we have multipliers. And so on this occasion, what we need to do is we need to put a 2 in front of the HCl, because what that does is that multiplies the one hydrogen by 2, so we get 2 hydrogen. And that matches with the 2 hydrogen in the products. And we've also got 2 chlorine, and we've got 2 chlorine in the products as well. So this equation is balanced. In the second equation, the big temptation that we must not do is to put a little 2 after the O in H2O, because that changes water into hydrogen peroxide. And through balancing, you cannot change the nature of what something is. And so to get those 2 oxygen that we need on the right-hand side, we put that multiplier in front, but we have the problem now in that that 2 multiplies the 2 hydrogen by 2, so we've actually now got 4 hydrogen on the right-hand side and only 2 on the left. So we need a second multiplier on the left-hand side, and then this one is balanced. Then we get a little bit more challenging in the third one, because what we've got is 2 and 3 for the chlorines. They are the unbalanced element. And so what we have to look for here is a common multiple of those two numbers. And the common multiple of 2 and 3 is, of course, 6. So by putting a 3 in front of the chlorine on the left-hand side, we have got 6 chlorine atoms. And so we need to put a 2 in front of the chlorine on the right-hand side, the aluminium chloride on the right-hand side, and that gives us 6 chlorine as well. And then we have actually made the aluminium unbalanced, and it was balanced at the start, but it's now unbalanced, and so we need a 2 multiplier in front of the atom of aluminium on the left. And then the final one for the combustion of propane, we've got oxygen in lots and lots of places, and so my advice here is when an atom appears in lots of different places, leave it until the end, because otherwise you're just going to have a knock-on problem if you solve it one at a time. And so we should solve, first of all, the 3 carbon atoms on the left-hand side by putting the multiplier 3 in front of the 1 carbon on the right-hand side. And similarly, we've got 8 hydrogen on the left. We only have 2 hydrogen on the right. So if we put a 4 there, we've now got 8 hydrogen on the right-hand side. And now we have got 4 lots of 1 oxygen, which is of course 4, and 3 lots of 2 oxygen, which is 6. 4 and 6 makes 10, and so we need to multiply our 2 oxygen on the left by 5 to get 10 oxygen atoms on both sides. Being able to calculate the relative formula mass, or MR, of a substance is something that underpins so many different aspects of A-level chemistry. The relative formula mass is found by looking at the relative atomic mass values of individual elements in a compound. And at A level, the relative atomic mass is defined as the average mass of an atom of an element compared to a twelfth of the mass of an atom of carbon-12. Now, at A level, these values are given to 1 decimal point. That means that we are acknowledging the existence of a greater variety of isotopes at A level than we needed to consider at GCSE level, where the majority of the relative atomic mass values were given as integer values. The principles are still the same though. When we're working out the relative formula mass of something, what we have to do is we have to take the relative atomic mass, and so for magnesium it's 24.3, and for oxygen it is 16.0. And so we have to sum those two numbers together, and so the MR is 40.3 grams per mole. For water, H2O, there is not just one of each element. We've got hydrogen, which is 1.0, but there are two of them, so it's 1.0 times by 2, plus the 16.0 for the oxygen, which gives us an MR of 18.0 grams per mole. And so we need to report that decimal point, even if the final answer is to 0.0. We do need to get into good habits. For the magnesium hydroxide, it's a little bit trickier because inside the brackets we've got oxygen and hydrogen, and outside the bracket says that 2. That 2 means 2 of everything inside the brackets. So I would suggest that the best way for us here is to just take the magnesium, 24.0. We've got 16.0 for the oxygen, but we need to multiply that by 2, and we've got 1.0 for the hydrogen, again multiplied by 2, which gives us an MR overall of the sum of all of those three numbers. So 58.3 grams per mole. Last of all, I thought I'd show you a slightly different formula, which is where you've got an ionic compound, magnesium chloride, and then you've got a chunky full stop after it, but then 8H2O comes after that. And what this is something called water of crystallization. And what that means is, in an ionic compound, we've got our 3D ionic lattice with positive and negative ions attracted to each other with that electrostatic attraction. But as well as that, we've also got some water in amongst those ions. And so what this formula is showing us is that for every 1 magnesium chloride, so that's 1 magnesium and 2 chloride, we get 8 water molecules in a ratio of 1 of the ionic compound to 8 of the water. What that means in terms of the MR is actually very little. It means that we need to take the 24.3 for the magnesium, add it to the 2 lots of 35.5 for the chlorine, and add that to the 8 lots of 18.0 for the water. So this is the only occasion where we use any big numbers for an MR calculation, when it's this water of crystallization. And so we sum all of those values together now in exactly the same way as we've been doing for the previous ones, and we get our final answer for the MR to 1 decimal point. You could also be required to calculate the percentage by mass of a particular element within a compound. And the percentage by mass calculation is where you take the relative atomic mass of that element, multiply it by the number of atoms of that element that there are in the compound, and divide it by the total MR for that compound. And because we want it as a percentage, we need to multiply it by 100. And so, for instance, if we look at these 3 quick examples where we're working out the percentage of oxygen in each of those compounds, now they are all the same compounds that we calculated the MRs for on the previous page, so we've already done half of the job, so we can focus on this new skill, which is where we take the relative atomic mass of the element, which is oxygen, so that is obviously 16, and we multiply that 16 in the first case by 1, so in other words it's just 16, and we divide that by 40.3, and then we multiply that by 100 to turn this into a percentage, and we get 39.7%. 1 decimal point, please, for percentages. In the second one, we're still working with oxygen, so it's still 16 for its AR. We're multiplying it by 2 this time because there's 2 oxygens in that total compound, and then we are dividing it by 58.3 and then multiplying that by 100, and so we get 54.9% as our percentage of oxygen within the magnesium hydroxide. And then last of all, we know our magnesium chloride has a total MR of 239.3. We know that oxygen is 16, but there is an 8 there, so there are 8 oxygens in this compound. And so we need to do 8 multiplied by 16 and then divide that by 239.3, multiply that by 100 again, and we get 53.5% oxygen this time. In quantitative chemistry, one of the most important concepts is the mole. It's important to note that a mole is just a word for a number. So in the same way that if I was to say, I have a pair of something or a dozen of something, you know how many of that thing that I'm talking about. For a mole, that number is Avogadro's number. So if I have a mole of carbon atoms, I have got 6.022 times 10 to the 23 carbon atoms. A mole of water molecules, I have got 6.022 times 10 to the 23 molecules of water. And so that number is just a number of things per mole. Now, the significance of the mole is that if you have a mole of any substance, its mass will be equal to the relative formula mass of that substance in grams. So 1 mole of carbon will have a mass of 12.0 grams. 1 mole of water will be 18.0 grams. And that works in terms of scaling up. If I've got 2 moles of carbon, it will be 24 grams. 2 moles of water, 36 grams. What I was using there, without saying that I was using it, was the relationship mass equals mR multiplied by moles. And obviously this has got 3 different formats. I suggest you remember mass equals mR multiplied by moles, because then when you want to try and rearrange it, for instance to make mR the subject of this equation, we just need to work out how to do that in terms of the algebra. We have to divide both sides by moles. And obviously moles divided by moles on the right hand side is going to cancel out. So we're left with mass over moles is equal to the mR. And similarly, if we want moles equals, we have to divide both sides by mR, and those two mRs on the right will once again cancel, and we're left with mass over mR is equal to moles. One of the ways that we can use moles is to balance equations, or to work out which of the equations we're presented with is the correct one. For instance, a question might say, in a car engine, nitrogen reacts with oxygen to make an oxide of nitrogen. And this happens in a car engine because of the really high temperatures that are reached. And we're told that 7 grams of nitrogen is reacting with 16 grams of oxygen, and we're told to work out which of these two equations is correct. Now, what we need to remember is, when we were balancing the equations, what this really is telling us is that 1 mole of nitrogen is reacting with 1 mole of oxygen to produce 2 moles of nitrogen monoxide. So there's 1 oxygen. And the second alternative equation is where 1 mole of nitrogen is reacting with 2 moles of oxygen to make 2 moles of nitrogen dioxide. And so our job then is to work out how many moles of nitrogen we're using and how many moles of oxygen we're using, and then match that to the correct equation. The method that we're going to use to solve this is something called the grid method, which transfers across a whole host of different calculations you can be expected to do. The first thing that we do is we write down the identity of our 2 chemicals that we're working with, which are nitrogen and oxygen. We then input, if we've got them, the masses of the elements in question, which are 7 and 16. We then calculate our mR values, which are 28.0 and 32.0 for the 2 elements. We calculate the moles that we've got present, so we do mass divided by mR, 7 divided by 28, which is 0.25 moles. And for the oxygen, 16 divided by 32 is 0.50 moles. And then the ratio, we can do it by inspection on this occasion, but what we need to do is we need to divide our moles, both of our moles, by the smallest value. So on this occasion, the smallest value is 0.25. So 0.25 divided by itself is 1, 0.5 divided by 0.25 is 2. So that means that the ratio of nitrogen to oxygen is 1 to 2, which means that the second equation is the correct one, because that has got the nitrogen reacting with the oxygen in a 1 to 2 ratio. Remember, if we don't have any numbers in a balanced equation, that means it is a 1. A second application of the grid method is something called reacting mass calculations. So for instance, in this question, we've been asked what mass of nitrogen is required to produce 100 kilograms of ammonia. So if we inspect this equation, we can see that nitrogen turns into ammonia in a 1:2 ratio. So in other words, 1 mole of nitrogen makes 2 moles of ammonia. So if we fill in our grid with nitrogen as one column and ammonia as the other, we can put those two ratios in that box. And then we're trying to make 100 kilograms of ammonia, which needs to be in grams, so that is 100,000 grams. And so once we've put 100,000 into this box, the last thing that we do before we start doing any real calculations is to work out the MRs of the two chemicals in question. And so we've then got our grid nearly populated, and what we need to do for our first step is to go down this right hand column to work out the one missing value that we don't have, and so that is moles. And so we have to take our 100,000 and divide it by 17, and we get 5,882 moles of ammonia. Then we have to look at the reacting mole ratio. 1 nitrogen makes 2 ammonia. And so what that means is the ratio of moles that we're calculating on the row above needs to mirror the 1:2 ratio that is from the equation. So we need to divide that 5,882 by 2. And when we do that, we get 2,941 moles of nitrogen. This is likely to be a 3-mark question. 1 mark for the moles of ammonia, 1 for the moles of nitrogen, and last of all, 1 for the mass of nitrogen. We've got the MR now, we've got the moles, mass is MR multiplied by moles, so 2941 multiplied by 28 gives us 82,348 grams. Now, supposing they'd asked for this in kilograms, it would therefore be 82.3 kilograms of nitrogen required. It's common in a chemical reaction to want to completely use up one of the reactants, usually because it's the most expensive reactant that you're using, but also sometimes because it's potentially dangerous if we don't use it up. And so this is called the limiting factor. This is the thing that is going to run out. But it's called the limiting factor because it's the chemical that limits the amount of product that you can end up with at the end of your reaction. Whereas the other chemicals in an equation are said to be in excess. Excess means that we've got more than we need of that chemical. It's like trying to do some baking and you've got half a dozen eggs and you're trying to make some cakes. If you've got 25 bags of flour, then the flour is present in excess and the eggs are very definitely the limiting factor. If we just use the example of the Haber process again, we can see by looking at this equation that the ratio that nitrogen reacts with hydrogen in is 1:3. What that means is, if we had 10 moles of nitrogen and 30 moles of hydrogen, nothing is present in excess. They will react together perfectly because that is a 1:3 ratio once you reduce it down to its simplest form. However, if we have 1 mole of nitrogen and 6 moles of hydrogen, hydrogen is present in a far greater proportion than the 3 that we need to react with our 1 mole of nitrogen. So that means that the hydrogen is present in excess and the nitrogen is limiting. If we were to have 2 moles of nitrogen and only 3 moles of hydrogen, well, the nitrogen is now present in excess, and we can prove that through justifying by saying that 2 moles of nitrogen would need 6 moles of hydrogen, which we don't have. We have less than the 6 moles of hydrogen that are required. And last of all, 5 moles of nitrogen and 20 moles of hydrogen. Again, it's worth looking at and saying, well, 5 moles of nitrogen needs 3 times that many moles, 15, to react with. We've got significantly more than 15. We've got 20 moles of hydrogen. So the hydrogen is present in excess and the nitrogen is limiting. Once you've worked out which chemical is present as the limiting factor, that is the factor that influences how much product we're going to make. And the product is the 2 in terms of the ratio. So that means that 1 nitrogen mole makes 2 ammonia. 3 hydrogen moles makes 2 ammonia. So in this first scenario, we can look at either of these values because there is no limiting factor here, or they're both limiting factors. Nothing is in excess. So 10 nitrogen will make 20 ammonia, and you can see that that mirrors the 1:2 ratio shown above. This time the nitrogen is limiting, so even though we've got 6 moles of hydrogen, we can only make 2 moles of ammonia because we only have 1 mole of nitrogen. This time the hydrogen is limiting. We can't make more ammonia simply because we've got more nitrogen. Once again, we're only going to make 2 moles of ammonia. In the final example, the nitrogen is limiting, and this time we can make 10 moles of ammonia because 1 nitrogen makes 2 moles, and so 5 moles will make twice as many, which is 10. An example of the limiting factor can be found in a reacting mass calculation. So for instance here, what mass of hydrogen fluoride can be made from 10 grams of hydrogen and 38 grams of fluorine? So our target is hydrogen fluoride, so we need to put that here. We've got to work with both the hydrogen and the fluorine, so this time our grid has got an extra column. From the equation, we can see that hydrogen reacts with fluorine in a 1-to-1 ratio. So we need to find out which of these 2 moles is the bigger number, and that's the present in excess chemical. So our hydrogen is 10, our fluorine is 38 for their mass. When we work out the MR, hydrogen is 2.0 and fluorine is 38.0. So moles, which is mass divided by MR, is 10 divided by 2 for the hydrogen. So we've got 5 moles of hydrogen, 38 divided by 38 for the fluorine. So we've got 1 mole of fluorine. We can see quite clearly that the ratio should be 1-to-1. We've got 5-to-1, which means we've got more than we need of the hydrogen. This is present in excess, which means this is the limiting factor. And remember, it's the moles of the limiting factor that influences the moles of the products that we can make. So the hydrogen fluoride is the 2 to the 1 of the fluorine. And so that means that for 1 mole of fluorine, we will produce 2 moles of hydrogen fluoride. The MR of hydrogen fluoride is 20.0, so our final task is to do mass equals MR multiplied by moles, so 40 grams of hydrogen fluoride can be produced. You'll notice that on this occasion, these 2 numbers, when you add them together, you get a bigger number than the 40, and that is because the hydrogen is not all used up. Only 2 grams of that hydrogen will be used up, and 8 grams will be left unreacted. The final thing that I want to look at in this video is concentration of solutions. Now, before we start that, a solution is when you take a solute and you dissolve it in a solvent, so some kind of liquid, and you make a solution. Typically, the solute is a solid, but it doesn't have to be. You can dissolve one liquid in another as well. Now, concentration is a measure of the amount of solute that is dissolved in a unit volume of solvent. And typically, what we are working with is 1 decimetre cubed of a solution, and the amount of solute that dissolves is normally in moles. So if we have, for instance, 2 moles of solute in 1 cubic decimetre of solution, the concentration is written as 2 moles per cubic decimetre, which is also equivalent to a litre, by the way, in terms of what a decimetre cubed is. Similarly, if we had a larger volume, 2 decimeters cubed, and we still had 2 moles, the concentration this time is 1 mole per cubic decimeter. And we can work that out using a bit of logic, because when we say per cubic decimeter, what we're really meaning is for each cubic decimeter. So if we've got 2 moles and 2 cubic decimeters, that is a concentration of 1 mole for each cubic decimeter, 1 mole per decimeter cubed. I said that concentration is typically in moles per cubic decimeter. It could also be in grams per cubic decimeter, and that works in exactly the same way. If we had 1 cubic decimeter of solution and there was 20 grams of sodium hydroxide dissolved in it, the sodium hydroxide concentration is 20 grams per cubic decimeter. If we wanted to convert concentration in grams per decimeter cubed into moles per decimeter cubed, since we've got the per decimeter cubed still in both cases, what we're really doing is converting grams into moles, or mass into moles. Now we know that to convert mass into moles, we have to divide it by the MR. So you can convert a grams per decimeter cube concentration into moles per decimeter cube by simply dividing by the MR, which for sodium hydroxide is 40.0, and so the concentration in moles per decimetre cubed is going to be 0.5 moles per cubic decimetre. And it works the other way as well, of course. If you want to go from moles per decimetre cubed into grams per decimetre cubed, this time we have to multiply by the MR. And that makes sense because mass equals moles times by MR. Okay, I hope you found this Head Start video useful. If you want to find out more about A-level chemistry for this topic, check out some of the links in the description. If you found it a bit tricky and want to go over this topic a little bit more slowly and in more detail, I'll put links to my GCSE explanation videos in the description as well. But that's all for now. I'll see you again soon.